Hi everybody, I'm AG, and in Unit 5 we are going to introduce a subject called combinatorial analysis. From the common sense, the start point is considering events in daily life that are not simultaneous. Events like A that occurs in, let's say, m possible ways, and B that occurs in n possible ways. There will be m plus n possible ways to produce A or B. Remember the OR operator. Now, if these two events are very related, there can be a product on m and n ways to produce A and B. Remember the AND operator. Let's clarify this concept with an example. Extending the idea of an event on ordering a product, we have three sets. The first with 3 drinks, the second with 2 foods, and the third with 2 additionals. If a customer wants to order one single product, can be 7 different orders. Can be only a beer, only a fries service, etc. If the customer wants a combo with one of each type without considering the final order of the combo, can be 12 different combinations. If considering the final order sounds familiar to you, is because it's what we did before with permutations. Rearranging the elements, there will be 72 possible combinations. The product rule by the 3 factorial, and that is what combinatorial analysis is about. Control on these outcomes. Solve the factorial of a big number is sometimes kinda difficult. Most calculators have this function. If not, use this expression instead. We are going to find the 6 factorial manually and find it with the Stirling's expression. As you can see, there is an error range on 1.3%, so take care on the error propagation. Here is when we introduce the idea of a k combination on n elements. Without considering the order, we take k elements on n element set. In most cases, scientists refer to this as the binomial coefficients, or n over k case, and this is the way to find it. So, if a customer wants to serve its own 2 items menu, there will be 10 combinations, and that's it. We don't care about the final order because it's not a permutation, it's a combination. A permutation in a set of n elements is any order rearranged. Now, what happens if we take only certain number of elements? Let's say m. We clearly have more options over n elements, and this is called an m-permutation on n elements. The number of outcomes is given by this expression right here. In that way, a 2 permutation on 5 can have 20 different results, and a 3 permutation on 5 can have as much as 60. Until this point, all permutations we have seen are considering in a set of unique elements. But what happens if we have duplicate elements? This is called a permutation allowing repetitions. The number of outcomes is given by this expression right here. On the top, the factorial of the total number of elements including duplicates, and below the factorials on the duplicate elements. By example, 6 on the top and 2, 3, which is for the red and normal Coke and the pork kettle or gut burger respectively. On this menu, we are going to have as much as 60 different outcomes. The idea of a repetitive element takes us to the idea of a sampling an ordered set. Sampling m elements in an n set without replacing them is the same idea behind an m permutation on n, right? What happens now if we replace the element each time we take the sample? This is called an R sampling on an n set with replacement, and there will be as much as n to the R samples. These are all the possible results for a replacement 3 cards sample on this 5 element set. Because a card plate like this allows duplicate letters and numbers, this can be seen as an ordered sampling with replacement case. Let's suppose this position right here doesn't allow 1 or 6. How many card plates within this format can exist? Remember, there are 26 letters and 10 digit options. As we saw before, the number of samples is given by n to the r, and each position will be under the basic product rule. So one by one, let's see what can be placed here. Each letter is among 26 options, and this position can hold only 8 digits. These two positions will hold up to 10 different digits. Grouping this and that, we find that the number of possible card plates is among hundreds of millions. Also, combination of elements and events can be graphically expressed throughout 3 diagrams. By example, when a penalty shootout enters into the sudden death, we arrange all the possible outcomes. In this way, on the left side, what will happen if each team scores without fail. In this case, anyone who fails first loses. On the right side, what will happen if nobody scores? The first who scores win. We did not extend the series beyond 3 shots because usually somebody fails and the game ends.
Alto, il campionato del mondo è finito, lo vince il Brasile.
If you pay attention, as always, you are going to approve the following test. Let's go. In this fruit universe, we have 3 sets, A, B, and C. Question 1. In how many ways a single fruit can be chosen? Question 2. We want to take a single fruit from each set. In how many ways can be done? Question 3. We want the yellow ones. Banana, peach, and pear. In how many ways can be done? Question 4. Choose 2 different fruits for a juice. How many options you have? Question 5. We want to give a collection with unique fruits to someone. With 1 fruit from A, 2 fruits from B, and 2 fruits from C. How many options you have? By the sum rule, there are 14 different fruits to choose. If we want 1 fruit for each group, by the product rule we have 100 different combinations from A, B, and C. And also the final order can be first A, second B, and third C. Or maybe first B, second C, and third A. So there is a permutation involved. 3 factorial by 100 give us 600 different options to give the combinations. We want the yellow ones, which are 3. So this can be like this or that. There are 3 factorial different ways to give the yellow ones. We want 2 fruits from 14 to make a juice. If we consider the order is a 2 permutation over 14, as much as 182 different ways to give the juice fruits. Finally, we want a selection from each group, and we don't want duplicates. This is an ordered sampling without replacement. We find the number of samples of each group, and by the product rule give us 600 options. Also, again, the order in the group selection is a permutation. 3600 different options for the last question. Now let's solve the same questions, but this time we don't care about the order. By example, if someone asks you 2 fruits for a juice, you give like this or that. It doesn't matter, okay? The question 1, the order is not relevant, so still 14 options to choose 1 single fruit. In the question 2, still 100 options to choose a fruit from each group. And that's it. We don't find a permutation across the 3 groups. Now, in the question 3, if we don't care about the order, there is only way to choose the yellow subset. The answer here is 1. In the question 4, without order considerations, we get rid of a bunch of options, and the idea is a k combination on n elements, or an n over k case. So 91 options to make a use. The same way in the last question. This is the idea behind a k-permutation on n elements. 300 options to give a present. Last question. Express graphically the permutations or the F set using a tree diagram. This has been all for Unit 5. By the way, if you want more advanced exercises about this unit, a link in the video description will be available. Thank you very much for watching our video and see you on the next unit.